Good morning, everybody. So welcome to the second day of the summer school. Today we will make the first introduction to the neural TTS. So we have learned the target is, again, we have to keep in mind what is the target. The target is the conversational TTS. Conversational TTS, I repeat here myself, means how to use TTS inside the conversational agent. And a core component of the conversational agent is the dialogue system. So yesterday we have heard a lot about the state-of-the-art dialogue systems, okay? And the output of the dialogue system is the natural language generation. It's part of the dialogue system. That text comes now as input to the speech synthesis systems. Now, what we would like is to extend the input, to include not only the text, but the way that we want to say that text in a dialogue. That will require more signals, actually, to get from the speaker who interacts with the system, apart from his or her words, but also the way that he and she says that. Nevertheless, once that information comes into the system, then the system has to do two major parts. Do a linguistic to acoustic transformation. First of all, the text is transformed to linguistics. And then that linguistics, as it is an input to a first system, now we use it, it is mainly a sequence-to-sequence mapping, and one example of it is Tacotron. Then from these acoustic features, we do another mapping to the samples. So that is exactly the part, the Tacotron, or let's say the sequence-to-sequence mapping from linguistics to acoustics, and then from acoustics to samples in a neural based speech synthesis system that Vassilis will explain to us today. Okay? How to control more the speech synthesis system, it will be shown by Matt tomorrow, to how we impose a certain speaking style, which is very important component of the conversational TTS, and how then we can also make other modifications. That is Tomoki Toda on Thursday. And on Friday, how can we evaluate all this? Okay? So, with that, I'd like to, so Vassili, you can start. So, this here. Okay. Great. And keep in mind that you can use your microphone. It's very important that you use the microphone because everybody can hear you, but also we record all the sessions. So we want also other people who will see these videos to be able to understand what was the question, to be able to listen to what was the question, and then the answer from the speaker. Okay, so please use the microphone. Don't be afraid to interrupt. This is very important for the communication, okay, and understanding.
Good morning. We will talk today about neural speech synthesis. First, I will start with neural vocoders, and I will describe an implementation of Wavenet. Since the introduction of Wavenet in September 2016, many other neural vocoders appeared, so that apart from Wavenet today, I will also describe briefly the Wave RNN, which is a practical autoregressive neural vocoder, and the parallel Wavenet, which is a flow model which can produce speech from noise in one step. The revolutionary thing about WaveNet is that it models the raw waveform, and it was the first time that this has been done in this area. The idea started, we want to encode the probability that some sequence encodes speech and separate this from sequences that encode noise. If we had a function that can distinguish between speech and noise, that could have been a very useful function which allows us first to recognize speech and second to generate speech. This probability, which gives high probability if this sequence is speech and very low probability if this sequence is something else, not speech, can be factorized using Bayes' rule into this sequence. The conditional probabilities are much more stable numerically to model than this joint distribution. This is much more stable because actually this can be written into that way, and since it is numerically much more stable, we will try to model this probability distribution, the conditional probability of sample at time t, given all the previous samples. Let's start how we transform the input to WaveNet, to the original WaveNet, which first appeared in 2016. Let's suppose that we have this raw audio sequence. This raw audio sequence belongs to the range -1 to +1. This sequence is first transformed into a sequence x1, xt, and so on, using an mu-low transformation. This mu-low transformation, it does... This is the laser? Yeah. This mu-low transformation does dynamic range compression so that it distributes the signal into, for example, the signal as it is, if you plot the distribution of this signal, most of the samples are around 0. So the probability, the histogram is very highly peaked around 0. After this transformation, the histogram is becoming more, how to say, wide, and also this distribution, where M is that, it can put the values into the range. We do also a quantization, and the xt values are quantized into 266 values from 0 to 255. Finally, the xt value is encoded into one hot vector. I will have an example here to explain what is going on. Let's suppose that this is a signal. The signal, after an mu-low transform, it is transformed into this one, and after it is quantized into 4 bins, it will take values 0, 1, and 2, 1, 2, and so on. And we transform that into one hot vectors. For example, in bin 0, since this is 0, we put 1 and all others are zeros. In bin 1, it's 1 and all others are 0. In bin 2, it's 1 and all others are 0, and so on. And this is the input to the WaveNet. So the input to WaveNet is this matrix here. Now, how we will model this conditional probability? In the original wavenet, they model this conditional probability with a stack of dilated convolutions. We can also model this with recurrent neural networks, as I will show you in the next presentation. Let's now see the architecture of wavenet. First, I will describe the 1 times 1 convolutions. These actually are matrix multiplications, and their use in the code is the following: to transform from an n-dimensional space to an m-dimensional space, so that to change the dimension. This is their use. For example, if we have this signal which has 4 dimensions and we multiply with this matrix, the output, the time dimension remains. This is the time, this is the feature dimension. So we change the feature dimension. The time dimension remains, but the feature dimension is 3 while the input was 4. So the 1 times 1 convolution are actually matrix multiplication which map from one space to another space with different dimension, which has different dimension. Let's now explain how the causal convolution works. Let's assume that we have this signal here, this input here, and we have this filter. Usually in signal processing, when we want to do convolution, we flip the filter. In machine learning, flipping the filter is not important because the weights of the filter are learned. So it's not important to flip the filter. Now let's assume that we have this filter and we apply it to this input signal. We multiply 1 times 1, 2 times 2, 0 times 4, we sum all of them and the outcome is 5. And we repeat it to the next, we move 1 time step and so on. So this is the output signal. Causal convolution these are the convolutions. The causal convolutions do not consider future samples. For example, in that example, we consider this is our time step. We also consider sample 1, which is in the future. So this convolution here is not considered as causal. In the original version of wavenet, we use filters of width 2. So this is the present and this is the past. So by construction, the filter does not have future weights in the future, so it is causal by default. And now I will explain what are the dilated convolutions. Let's assume that we have this filter. This filter has a range of three samples. In order to increase the receptive field of the filter, we can do the following. We can insert some zeros here. So now the width of the filter is 5 and the receptive field is bigger. And if we apply that, we see that all that samples contribute to the outcome. And so on. However, in that case, we do some unnecessary multiplications. For example, the multiplication of 3 with 0 is unnecessary because we know the outcome, it is going to be 0. In order to have the same effect like that without doing the unnecessary multiplications, we use a trick which is called dilated convolutions, so that we only multiply this with this with 2, 1 to 1, and they sum that without considering the multiplications with 0. So dilated convolutions is a clever way to have filters of larger receptive fields and at the same time to reduce the computational cost. And now is an example. The previous example was one-dimensional. Here is an example where the input signal is not one-dimensional, but it has the feature, it has 4 features. So now the filter has to be a matrix. And I will not spend so much time on that because we have much more important things in the next slides. Here is how the output is produced by multiplying the input signal with a filter in that example. And we can see just how it is going, how it works. And this is another example as before, but now we do not simple convolution, but dilated convolutions. And let's see the general architecture of Wavenet. Wavenet models the conditional probability with a stack of dilated convolution. And the flow of information, it is visualized here. For example, let's suppose that these are the input samples. First, we have a residual block with dilation 1. So the output here takes information from this sample and the sample which is one step to the past. And all the samples can be calculated in parallel. The next layer takes to compute this sample, we take information from this and from this, which means we need all that input samples. All that input samples contribute to the computation of this. And all that samples can be computed in parallel, since it is we use convolutional neural networks. In the next level, we have a dilation 8, and now the receptive field is all that. So the dilated convolution allows us to increase the receptive field exponentially with the depth or height of the network. If we used a convolution without dilations, in order to have the same receptive field, we needed very high network here, very deep network. For example, the receptive field of this example, of the whole example, is this one, which is 16. In Wavenet, in the original paper of Wavenet, the dilation is doubled for every layer up to a certain point and then is repeated. So we have 1, 2, 4, up to 512 dilation, and then we repeat it and repeat it and repeat it. And this is another example how this works after one block of dilations follows another block of dilations. And now I will explain the residual connections. What is the use of the residual connections? In order to train a wavenet with more than 30 layers, residual connections are used. Residual networks were developed by researchers from Microsoft Research. They formulate the mapping function x to the output of this function f to x between the layers from f to x like that. For example, the f to x tau is not the output of the layer, but is the input plus the residual, the small difference that the layer does to the input. From the mathematical point of view, this transformation is trivial. It says nothing. It's a trivial transformation. It gives nothing. From the engineering point of view, it has very big advantages because it helps the optimization algorithm and also helps us to find very good initialization weights for these layers inside the residual connections, because we want the residual signal to be a very small one close to 0, so that we can initialize these weights very close to 0 as well. Also, during the backpropagation, we solve the gradient vanishing problem. because as the signal, the derivative is back propagated in order to update the weights, in every layer that it passes through, it loses some information. So after a lot of layers, it contains noise. It does not contain useful information anymore. However, using that construct, one part of the derivative passes from here, and the derivative without modification passes also from this connection back. So it does not lose the information. It still contains information because it passes through these identity connections backward. So it is very important, the residual connections for the optimization. Now I have two residual blocks, so the derivative passes from here, so that now it is very strong and can update the weights in this layer, and also passes from here and updates the other layer below that, and so on.
Excuse me. So each 30 layer there is a residual connection?
For each one of this layer there is a residual connection.
Okay.
One layer, residual connection, one layer, residual connection, and so on. And inside each block, I wouldn't call it layer, I will call it block. In each of these 30 blocks, or even more than 30, we have this construct here. This construct can be considered as an expert gate. The expert models some part of the space, of the hidden space, and the gate gives a rank how valid is the information that the expert provides. So then we multiply these two. If the gate is close to 0, the information from the expert is not passed because it is 0. If the gate is close to 1, then the information from the expert, it is considered valid and pass through that connection to the next block. And how we model the output? The output layer of the network has 256 output neurons, output units. And we use a softmax, which actually is like that. The mathematical formulation of softmax is this. And what it does is that it transforms the output of the network into a categorical distribution where each one of the 256 categories has a probability. So consider a histogram, something like a histogram, and all the values sum to 1. Now let's see how it operates, the wavenet. Here is an example with a receptive field 3. This is the input speech. This is the speech. Have a look here. In the input, we don't consider the last sample. We only consider all the samples minus the last one. The first 3 are used to predict a probability distribution for the next sample. Because our receptive field is 3, these 3 are used to predict probability distribution for x4. The target distribution is x4 itself. So we have two distributions. This one, which is a categorical distribution with 256 values, and we have some probability in each one of this category. And this one, which is one hot encoded, which has probability 1 in one of the bins and 0 in all other bins. I have seen some papers now that we may improve the robustness of the training of this kind of autoregressive encoders if instead of using one hot encoding in the target, to use 1 in the bin 1 minus epsilon in the bin we want, and some small values in all other bins, which all of them sum to 1, so that even in the 0 give a small probability, and this gives robustness to the noisy speech input if we want to model noisy speech, or if we want to model many different speakers and situations. Here, the P4, as I told you before, is the modeling of this probability. This is the conditional probability of sample X4 to fall into one of the 256 categories, given all the previous samples. And the next probability is this one. In our case, in the original formulation, we should have also included here the X1 sample, but for practical reasons, we have a receptive field and we neglect all the samples which are outside this receptive field. The receptive field, it is defined by the dilated convolutions, of how many dilated convolutions we have and how big each one it is, how long it is. And now we will see how we will model the loss function, because we have this output of the network and this is the target. If we have two distributions and a very good loss function to measure how close this distribution is to this distribution is the cross entropy. So we use the cross entropy between the prediction of the network, which is PT, and the target distribution, which is our initial speech shifted one-time samples. Have a look here. In the input, the last sample is missing. However, in the target, the last sample is included. We lose the initial receptive field samples here. And now let's see how the audio is generated with Wavenet. I will continue with receptive field 3, and to make it more clear, I will not have 256 quantization channels, but only 4 output neurons, 4 quantization channels. So the input is this one. Initially the input is randomly initialized, or just put all of them to silence, which means 0, or the mean value of 256, which is 128, the mean value of that. So we put this input as this is the input to Wavenet, which produces P4. This is the output of the network, which is a probability distribution over the cycles 1, 2, 3, 4. And next, we sample from this distribution one value. Let's suppose that we throw a dice and we sample this one. The next sample belongs to this category. This is used in combination with the previous two as an input to produce a prediction for the probability of distribution of the next sample. We also sample this, we sample from this categorical distribution, and let's assume that the dice was 0, and so on. We keep on continuing. So the whole procedure is autoregressive, and because we produce one sample at a time, it is slow. The sampling method that have been proposed is the direct sampling, just sample from this probability distribution, the temperature sampling, the mode sampling, which take as a sample the maximum of the previous values, the mean sample, which take the mean of the distribution, the top K sample, and so on. From my experience, the direct sampling, which is the easiest one to implement, or one of the easiest one to implement, is also the one that works best in most situations, followed by temperature sampling. After we have produced a sequence of samples, the samples are scaled back to speech with the inverse mu law transformation, and we have the speech signal. If you try to produce speech using the whole network as it is, in order to generate 3 seconds of speech, you will need 1 or 2 days. So it's very impractical. An algorithm appeared very quickly after the original WaveNet paper was published. It was from a PhD student, Tom Le Pen, which says we don't need to recalculate everything in every time step. We can cache some previous computed values and just compute this one and use the cached value and sum these two in order to have this output here. By using caching, the 3 days, the 1 or 2 days of generation reduced to about 3 minutes, having an implementation, a relatively fast implementation. And now the algorithm made practical for research purposes. It is not still practical for production because you need 3 minutes to synthesize 3 seconds of speech. But anyway, for research purposes, it is practical. Now I will describe the high-level architecture of WaveNet. Here is the input. The input is passed from an initial 1 times 1 convolution. The purpose, which in the paper is called causal convolutions, the purpose of these convolutions is to transform the dimension of 256 to another internal representation. Then we pass all that residual blocks, 1 block at a time. In the original implementation of Google, Google never published their parameters. However, from some presentations, I found that in their original architecture, the residual connections, the width of the residual connection is 212, the number of layers is 30, and here we have some skip connections. What's the use of skip connections? Instead of getting information only from the last layer, we get information from all layers and we sum all of them together in order to make the final decisions. Why we do that? Because in each layer we need a multi-scale architecture. Each of this layer encodes a different part of the speech. For example, this layer encodes samples which are very close together, while this layer encodes samples which are very fast, very far one from the other. So by having all that skip connections, we get information from all that features that are close together, from samples that are close together and samples that are very far away. So we get all of them, we sum them, or we may even multiply with a matrix, and then we pass through a postnet. The purpose of the postnet is to change this output a little bit so that to resemble more to a probability distribution. And then the final, the softmax gives the prediction of the sample xt given all the previous samples up to the receptive field of the network. And here is another picture which describes the architecture. This is the input. This is some preprocessing MU low transformation and one hot encoding. This is the causal convolution to change the dimension of the quantization level to the residual levels. This is the block with the residual connection. And these are the skip connections, and all of them are used as an input to the postnet to give us the prediction. And the loss function takes the prediction of the network plus the input shifted one sample in the future and compares these two using cross entropy. If we use this one without conditioning, the result will be a bubbling noise. I will play you some samples later on. If we want to encode a speaker, the identity of a speaker, we may use speaker embedding. Speaker embedding is just a matrix with some random initialized rows, and the speaker chooses if the speaker are just, the G is just number 1, 2, 3, 4, 5 to the number of speakers, and if, for example, speaker 3, we want to generate speech of speaker 3, we choose the third row of this randomly initialized matrix. However, this matrix is also learned during the training. So we pass from some, we multiply this, this row with some other matrices in order to change the dimension, and we also add to the residual block. We may even simplify that by avoiding this multiplication. However, this works better than this one. More important is to encode linguistic information, because we want to map text to speech. And this is called local conditioning. Local conditioning, linguistic information, it is measured with a different time clock. For example, speech, it is sampled with a sampling frequency, say 16 kilohertz. However, the linguistic features are measured in every frame, which might include, for example, we can sample it every 5 milliseconds. So we have different sampling rates. For this reason, we have to upsample this one so that the sampling rate of the linguistic information to match exactly the sampling rate of the speech. And we may use the multiplication with matrices or without matrices. The previous one works better. Or we may use also 2 multiplications and so on. These are some ideas. And we can have at the same time both local conditioning and global conditioning, the speaker ID and linguistic information at the same time. And now it is a picture of how the whole thing works together with some linguistic information. We do upsampling, and we have some other convolutions here which are added and pass through the expert and through the gate and so on. Because the wavenet was very slow, many improvements have been suggested. One improvement is the following. Instead of multiplying all the outputs with these matrices and then sum, we can concatenate them and then multiply with a very big matrix. This can save up to 10% of computational time. Also, another idea is this one. Instead of having different convolution here and different convolution here, we may have one convolution and split. This can save, this is a tremendous amount of saving. If you train a model with this one, you may need 2 weeks, and with this one, instead of 14 days, you will need only 9 days. So that the amount of computational saving is huge. Another idea is just to avoid altogether this convolutional one-to-one. However, this one has some effect in the quality. The previous one are improvements that does not affect at all the produced quality. This one that I show you now affects the quality. Another improvement is, which also it can make the wavenet a little bit faster, is instead of having filters of width 2 and dilation 2, we can have filters of width 3 and dilation 2, which I show you how they operate. Here we have of 3. One may say, okay, but if we have filters of width 3, how can we simulate causal convolution? It's very simple. We just shift the output. For example, we assume that our time step is this one and all this filter is in the past. Just by shifting, we can simulate the causality of the filter. Some other improvements is the following. This appeared in a paper, in the paper of parallel wavenet. The original wavenet produces a categorical distribution with a softmax. Okay. One idea is, instead of producing this categorical probability distribution, to have a network which predicts parameters of a continuous distribution. For example, in the paper of DeepMind in parallel wavenet, they use a mixture of discretized logistic as an output. So the network actually predicts these mixing parameters, the mean value of each logistic. Let's assume that we have 10 logistics. These are the mixing parameters of the logistic, these are the means of the logistic, and these are the scales of the logistic. And they use this construct here because they operate not in the probability density function, but in the cumulative density function, because they this comes from a paper of Pixel CNN, and this cumulative density function was shown to be much more stable. I will explain you about this stability in my next slides in the pixels. However, in wavenet, I don't think the produced results of this discretized mixture of logistics that are better than if we use mixture of probability density functions of logistics. I mean, the probability density functions may give better quality of speech. Another idea is to use mixtures of Gaussians instead of mixtures of logistics. And there have been quite a lot of papers using that. If we, instead of producing, okay, when we have the categorical distribution output, the loss function was the cross entropy. Now, the loss function, if we produce parameters of a continuous distribution, can be seen that actually is a log likelihood function, the loss function. It is the cross entropy, but it is it can be written as the log likelihood function. Here are some samples. The first one was of my original experiment 3 years ago. I trained a wavenet without any conditioning. The wavenet learns noise, but noise has characteristic of human voice. Let's hear it. It's babbling noise, it says nothing. It has no linguistic information, but it sounds like human. It's noise that sounds like human. If you plot the F0s, the formants, everything appears there. It does not have meaning inside to convey. It does not convey information, but all the others are human-like. This is my second experiment 3 years ago. Here I used as local conditioning TTS linguistic labels produced by a front-end system. So the front-end system produced the linguistic information and the wavenet was used in the pipeline of statistical parametric speech synthesis as both the statistical model and as a vocoder. Okay, the quality is not very good for many reasons. One reason was that the database was very small one. The other reason was that the quality of the labels that I produced with the front end was not very good and contained a lot of noise. Let's hear how it sounds. It was just the first.
To make matters worse, the state's largest malpractice insurer, OHIC, announced in March it will no longer renew policies for Wyoming doctors.
You can hear some background noise inside. However, now it conveys some information. That was the original proposition of Wavenet, to use linguistic features and use the Wavenet both as a statistical model and both as a vocoder. However, people realized sooner that if we use the Wavenet only as a vocoder and insert conditional information, not linguistic, but just speech feature, such as spectrogram or male filter banks or Kepstral coefficients, then the quality is much, much better. And now I will play you some samples which were produced when we consider Wavenet not as a statistical model plus a vocoder, but only as a vocoder, which takes as conditional input the speaker identity and male frequency band and produces speech.
Author of The Danger Trail, Philip Steele's, etc.
Can you show us which one you play?
It's this one. Now I will play this one.
Author of The Danger Trail, Philip Steele's, etc.
It's the same model. I just changed the speaker identity in each one.
Author of The Danger Trail, Philip Steele's, etc.
Author of The Danger Trail, Philip Steele's, etc.
Now is this one.
Author of The Danger Trail, Philip Steele's, etc.
Now is this one.
Author of The Danger Trail, Philip Steele's, etc.
Now is this one.
Author of The Danger Trail, Philip Steele's, etc.
And if we change the filter bank to another sequence,
How can you manage all alone, Mr. Young?
and so on. It's not, I will not play all of them. The sampling here is the sampling rate and all the parameters that I use to produce that.
Author of The Danger Trail.
What happens here? And F5.
Click on the appropriate timer.
Okay. Now we'll describe some
Excuse me?
problems with Wavenet.
Sir, how many hours for each speakers did you have in your database?
It's the Arctic database. It's slightly less than 1 hour because I use some part for training, some part for for test, and some part for evaluating how the training goes on. So it's less than something like, for training is something like 40 minutes, 45. So it's a very small database actually. It's a very small database. But even with a small database we can produce. However, people very quickly realize that the Wavenet produces some artifacts. And there is a paper of Wu et al. Which is called Collapsed Speech Segment Detection and Suppression for Wavenet Vocoder, which says it gives some heuristics that if an artifact is produced, just cut this part of the signal, throw it, and substitute this part from a traditional vocoder. I didn't like that idea very much, actually. Anyway, I like that they identify the problem and they categorize these two kind of artifacts. Artifact type 1, which have noise, this zzz noise, and type 2 artifacts which have some clicks, which here it is here like that. Type 1 artifacts are produced when the output of wavenet is parameters of a continuous distribution. And type 2 artifacts are mostly produced when the output of the network is the softmax.
I have a question. Does sampling with a temperature help reduce these artifacts at all?
It helps a little bit, it helps a little bit with this artifact. It does not help at all with this. However, I will concentrate, we can, a little bit helps with this one, the temperature sampling. But I will concentrate now how we can solve this kind of artifacts. This is because this kind of network that produce parameters of continuous distributions are very important because these networks are used as teachers to teach the parallel wavenet. So they are very important. So I will concentrate on type 1 artifacts. Type 1 artifacts is not a sampling problem. It's a characteristic of the trained model. So the trained model has this characteristic inside. They are instabilities which are related with the form of the loss functions in combinations with speech audio segments that have very small variations. For example, silence segments. And we will see what happens. Let's see the cross-entropy loss functions when we have a softmax probability distribution output. The cross-entropy is this one. If we plot as a function, if we plot this one, the cross-entropy actually penalizes the small q's and tries to increase all these qi's. If we see the negative log likelihood function, the negative log likelihood function, let's suppose for simplicity that the output is a simple Gaussian with 0 bits and this scale parameter variance. The mean value is not very important for our analysis, so I will concentrate on variance. So the log likelihood has this form. It has two terms, this term and this term. If we take the derivative, which is actually the value which is back propagated to change the values of the network, has this form. And I plotted this one. So H rewards small sigmas for samples which are within a few standard deviation. For example, if the sample is close to 0, close to the mean value, so close to 0 in our case, which 0 is our mean value. Close means not very far. For example, 2 standard deviation at most apart from that. Then, if we plot this function, we see that H rewards the small sigmas. However, if we are very far away, a sample is very far away from the mean value, in our case the mean value is 0, then this function penalizes the small sigmas. So we have a strange behavior. When the sample is close to the predicted mean value of the distribution, it rewards small sigmas and pushes the sigmas to become smaller and smaller and smaller. And then, if a value appears that is far away from the mean value of the predicted distribution, it penalizes that and penalizes with very huge values of penalty. So we have this situation here. So if the samples that appear are very close to the mean value, it pushes sigmas towards this direction, smaller and smaller and smaller. And finally, when sigma is very small, a sample appears which is very far away from the mean value from the predicted mean value, and this produces huge updates of the weights and sends the weights of the network very far away, possibly to infinity, and the training diverges. So if we compare the cross entropy loss with negative long likelihood loss, we see the following. The negative log likelihood loss in combination with data segment of a phoneme that have very small variation across the database push the scale parameters towards zero as the training evolves. Then, whenever an outlier sample appears, it throws the parameters of the network very far away from their optimal values. Then the optimization may get stuck in local optima very far away from the optimal values and the training fails. On the other hand, the cross entropy does not have this instability mechanism. Whenever a sample appears, which belongs to a quantization class, then the weight of the network are slightly pushed so that to increase the predicted probability of that samples. The probabilities of all other classes implicitly decrease through the softmax, because the softmax has to sum to 1. If you increase 1, the other has to decrease a little bit. But this is not unstable because they are the sigmas are reduced, everything is increased a little bit, and the others are reduced with a way that does not produce this instability mechanism. That's why using the softmax cross entropy loss as an output, we usually do not have type 1 artifacts. I will give you some examples having samples from the LG speech data set. This data set has some strange things inside. For example, it has some clips here from -1 to 1 and has some very long silence regions, which is ideal to test this instability mechanism. Here I train a network with cross entropy, and the training is stable, and I train with negative log likelihood and the Gaussian output distribution, and the training is unstable. Let's play that.
Printing, in the only sense with which we are at present concerned, differs from most, if not from all, the arts and crafts represented in the exhibition.
And the other one is very annoying.
Printing, in the only sense with which we are at present concerned, differs from most, if not from all, the arts and crafts represented in the exhibition.
For sure, you will not want a system like that in production. It creates instabilities. This is the type 1 artifacts that I told you before. How to solve these problems? The best solution, one of the best solutions, is using bigger and cleaner databases. However, this is not always possible because it's very expensive to have bigger and cleaner databases. The second one, which is used even in publicly available code, is to reduce the silence regions. If you download publicly available implementations of Wavenet, you may see that they cut silence in the front of the sequence and at the end of the sequence. And this helps to reduce the silence regions in the front and in the end of the utterance. You cannot cut the silence inside the utterance. It's dangerous. Another heuristic solution which works, and I have seen it in many papers, is adding noise to the data. For example, in the input data, put a little bit noise, and as the training goes on, reduce the amount of noise. That does not allow segments that have variance close to 0, so that to push the sigma parameters of the scale parameters, the predicted scale parameters to become very small. Another idea is to use dropout. Dropout is very, very important technique in speech recognition. It is also very important when you want to synthesize noisy speech. It helps a lot. It helps a little bit to reduce this problem even if you synthesize from a clean database. However, dropout not only helps, but sometimes it may introduce some noise in the output. So if you want to use a very clean database to synthesize speech, dropout may help in one sense and may also introduce some background noise in the synthesized speech. So one has to be very careful with dropout and with the dropout rate. So it's a good technique, but needs a lot of, fine-tuning. Another idea which is usually used in the literature and in the code which is publicly available is to clip the derivative values. For example, if the derivative value is huge, by clipping the derivative value, you may avoid this unnecessary, change of the weights when you do the backpropagation. However, this works, but the derivative, if this is the correct derivative, and this is the wrong derivative, if you clip that, okay, you clip so that it does not have huge value, but the direction is still wrong one. It's not the good. So this still can push you in the wrong direction. So it helps, this technique helps, but not always. And also, if you plot the loss function, especially if the database contains a little bit of noise, as it is in publicly available databases, you will see that the loss function is like that. Sometimes, in some samples, we have huge values of loss functions. So if we clip that loss functions before we apply the derivatives, so by clipping that we have this figure here, then, and we calculate before we average the loss function, this helps quite a lot, especially with noisy databases. It helps a lot to stabilize the training. Another idea which is used is to clip the variance parameter which is predicted from the network. For example, if this is very small one, do not allow it to be below a certain value. For example, I have seen in the literature that they do not allow this to become smaller than 10 to the minus 7, for example. And this works. Another idea is to add a term to the loss function that penalizes the small variances. Number 9 was proposed by Tim Salliman and Kingma, which is weight normalization and works very, very well, this technique. And another one, use large batch size. The batch size is important because during training, if we have a large batch size, we have segments, speech segments from very different parts of the databases. So if one is wrong, the other one are correct, so the mean value of that is not that much wrong. Okay, so the batch size, the large batch size is very, very important to stabilize the training. And I will play, before I played you that with the noise. This is the natural, this is with cross entropy. Now, if we apply a combination of the previous one, heuristics, I produce this one, which is much better than this one. Let's listen to this.
Printing, in the only sense with which we are at present concerned, differs from most, if not from all, the arts and crafts represented in the exhibition.
And this is the end of this slide. I will continue by presenting a little bit of another neural vocoder, which is WaveRNN, which is the state of the art in production because it is much faster. I will explain you the differences between WaveNet and WaveRNN and only a very brief introduction to that.
Yeah, so Vassilis, probably it's a good time now to ask for questions.
Yes, if you want, yes, for questions is a good time. Yes?
So as far as these big outliers go, why don't we just skip them altogether? Do we lose much?
To skip the outliers during training. But how you define an outlier during training? You just take data, you clear the data before you use them in a pre-processing, and then you just take the data and you feed it to the network. How you define an outlier?
Well, you anyway clipping. So clipping has a limit, right? So you have a way to identify what's above the clipping limit.
Okay. You mean clipping the derivative or clipping the loss function?
The loss function.
I say this helps very, very much by clipping the loss function. It is one of the heuristics. And in noise databases, it is one thing that you should always do.
So I guess my question is, if I anyway have to clip the loss function so much, do I get any useful information at all from this update?
You get.
Okay.
You get. Because if the loss function is something like that and there is an outlier here, the outlier, if you average all that, it is the outlier that dominates. So you get rubbish. If you reduce the influence of the outlier, still the outlier dominates, but its influence is reduced. Now, the information get from the other samples is important, because there are many of them and the outliers are few. There are not many. But if one is close to infinity, then the outlier dominates and all the others cannot recover from that. So clipping the loss function helps a lot. May I go to, yes?
Hi Vassilis, could you comment about temperature sampling, because it's supposed that could help with the noise, to reduce the noise, and you said that it was better to use just random sampling.
Okay, it reduces the noise when you have as an output the softmax, the categorical distribution. And it solves the type 2, not solves, reduces the type 2 sampling artifacts. And it is useful in that way. Okay, it's more complicated because you have to fine-tune also the temperature parameter, but it's a technique, I think it's the only technique that you can do to reduce the problem when you have a softmax output distribution. Okay. So it is important, with distribution that predicts, with a network that predicts parameters of a continuous distribution, I have not seen some works that the temperature helps. It may help as well, but I don't know.
Okay, thank you.
As I told you before, training of Wavenet is not practical for production. The generation of Wavenet is not practical for production. I have seen some works that they manage to make the Wavenet. For example, there is an NVIDIA implementation of Wavenet in CUDA that you may produce samples close to the real time. For example, 3 seconds of speech, you may generate it in about less than 3 seconds of speech, which is practical. However, there are other more practical autoregressive neural vocoders. One of them is WaveRNN, which was proposed also by, I think, by Carl Brenner and also by the members of Google, the team of Google. Here is the Wavenet. The Wavenet has a post-processing network and has these blocks of residual connections, and here is the expert gate construct and so on. To pass all that through 30 layers is very costly computationally. So the idea is to substitute all that things with only that thing here. So this is a recurrent neural network to substitute the layers of convolutional neural networks. We keep the post-processing network as before. You see that the difference? The post-processing is kept. Only this thing changes because we don't sum up all the residuals, so we don't need to pass through a non-linearity. And instead of convolution, we just have matrix multiplications because the dimension in a recurrent neural network is slightly different than the dimension in convolutional neural network, but this is just a technical issue, it's not important. It's not something important. So from the computational point of view, now we have much fewer multiplications and additions to do. So this runs much, much faster. One issue that in the paper of the paper that introduces the wave RNN was that the quality, if we have 256 categories as an output, may not be as good because we hear some quantization noise. There are many ways, many ideas how to improve that. One idea is the following. Instead of using 256 quantization level, to use more, for example 512 or 1024 or even more. However, above one level, if we use so many output neurons, then the training of the network becomes unstable. It's not stable anymore. So we cannot have as many output networks, output neurons as we want. Another idea was the following. To split the output into two parts. One coarse byte and one fine byte. So both together, so this is 8 bits and 8 bits. And if we concatenate them together, we have a 16-bit output, which is very high fidelity audio. And the architecture which is used here, it is a GRU layer, at least that was proposed in the paper. And in the paper actually it was the GRU the variant 3, which is described in this paper here, and it is this variant which is implemented in PyTorch. And also we had some masks in the input so that to prevent, I will show you later on what are the masks and why we need them. These are the masks here. I will not spend your time explaining you the technicalities. You will find that in the slides. But also you may as well train the wave RNN with another variant of GRU. For example, the variant 1, which is implemented in TensorFlow. If I have to compare variant 1 of TensorFlow and variant 3 of PyTorch, which is implemented in PyTorch, they have the following differences. The variant 1, the log likelihood loss reduces faster when we use variant 1. However, the variant 3 is something like 10 to 20% faster, runs 10 to 20% faster than variant 1. So they have some drawbacks and benefits by using the one or the other. And here is how we can use the masks, the input masks, in variant 1. One may also use an LSTM network as a wave RNN. So the kind of network is not restrictive. okay, the original paper used the GRU, but you may use any other kind of network that you believe that it can work well and does not have the gradient vanishing problems. These two networks are known that they have at least reduced the gradient vanishing problems. So let's see how the wave RNN is trained when the output of the network is coarse and fine bytes. So during the training we get this linguistic or acoustic information, this is the conditioning information. We get the coarse and fine bytes from the previous time step, and the coarse byte from the current time step, and we put it as an input to the network, but we have to take care so that the hidden state of the network will be affected, the first part of the hidden state, to be affected only by these two values, and this hidden state to be affected by all values. This part of the hidden state predicts the fine part of the network, and this predicts the coarse part of the network. And this was the training for this kind of output, coarse and fine. During generation, the generation of coarse and fine bytes is serialized. First, we put as an input the coarse and fine bytes which were predicted in the previous time step, initialized to zeros, for example, in the beginning. We pass through the first part of the network, which is related to the coarse prediction. We predict a probability for the coarse part. We sample a value for that, and then we use these sample values in combination with from the previous time step to predict the fine byte. So we have a serialized, so it is quite, is unnecessarily slow because we have to do all that transition. Another idea, which was not proposed in the paper, but I think it works much, much faster, is why to make our life so much complicated and have coarse and fine bytes? Just predict the output of the network. And this is much simpler to implement. It's just a recurrent neural network. Very simple, with two post-processing dense layers. So the input is acoustic information, conditioning information anyway, with the previous time sample, and the output is prediction of the probability of the current time sample, and then we use cross-entropy for training, or we sample from this distribution and we use the sample as an input during generation. And this was the wave RNN, which is very important because it is very fast. I don't know if I have to continue now with Yannis. Should I continue with parallel, or should we do 5 minutes now?
It's up to you. How much time do you think parallel?
Half an hour. Let's go to parallel.
It's better to have a break. But it's up to you again.
Let's have 10 minutes.
So, there is really also time.
Yes. Okay. Let's have a small break, because then we have to talk about parallel wavenet, and then about Tacotron. Are there any questions about wave RNN?
So have you tried your last approach to just predict the sample and not split to coarse and fine? Is the quality the same?
You may have as an output 512, for example. It's not the same, the quality, but the reduction in the quality is so small so that it doesn't worth to use the tricky implementation. Just a simple recurrent neural network can produce almost production quality speech.
Okay, well, thank you very much. Okay, so please sit down so that we will continue. Okay.
Now we will talk about an implementation of parallel wavenet. The original wavenet belongs to the class of autoregressive neural vocoders, as it is also the wave RNN. This kind of models, the original wavenet has parallel training, which means fast training, but sequential generation, and this is slow the generation. In order to make the produced speech, the generation process faster, many algorithms have been proposed. Today I will describe one category of algorithms in which the parallel wavelet belongs, which is an algorithm which is based in inverse autoregressive flows. I will explain you what that means. Here is the generation process of wavenet. This picture has been taken from the DeepMind blog, and as you can see, it's a sequential generation. One sample has to be generated to be used as an input for the next sample to be generated. And if we have to generate thousands of samples per second, this is a slow process. On the other hand, we can have this parallel wavenet. Again, the image was taken from the DeepMind blog about parallel wavenet. And the difference here is the following. Let's say that this is the parallel wavenet, and the parallel wavenet, it acts as a function which transforms the uncorrelated input noise into correlated speech in one time step. So you get the input sequence, you pass it through this function, this is uncorrelated noise, and you get speech in one time step. But how this works? This is based in a very basic theorem of probability. Even in undergraduate books they have this theorem in first or second year. For example, let's assume that we have an observed variable which belongs to space X. In our case, space X is the speech, the space of the speech signals. And we have a simple probability distribution on a latent variable. This can be, for example, a variable which can be in a normal distribution or in another distribution. And we have a function which maps from the latent variable to X. Then the change of variable formula is given by this formula, where the Jacobian, where this derivative is the Jacobian of f at point z. So from the latent space z, we get a variable, and through f we mapped it to another space x, and using the inverse transformation we can get from x one time point and map it to z. the distribution of the latent space is P to Z, which is known. For example, it can be the Gaussian distribution or the logistic distribution or the uniform distribution. The distribution in the observed data is not known here. There is one distribution, but we don't know this. So the function maps samples from the latent distribution into approximate samples X from the data distribution. This corresponds to exact generation of samples, because if we have some random samples in space Z, and suppose that we have this function f, then having this function we can map from these random samples to data space X, which is the samples that we want to have. So we can sample from the observation space. Having the inverse function, suppose that we know the inverse function, we can map samples from the data distribution into approximate samples from the latent distribution. This corresponds to exact inference of the latent state given the data. For example, from the data space, we have some samples, we don't know their probability distribution. We convert them into samples of the latent space, but since in the latent space we know the probability distribution of the latent space, which can be Gaussian or logistic or uniform, we can measure, for example, the log likelihood of these samples. For example, if one sample is has a big probability in the latent space, or it's an outlier, we can measure that because we have the probability distribution here. This simple observation is also applied here in speech. Given an observed data variable x and a simple probability distribution on latent variable, the problem is to find an efficiently computed continuous bijection f from the latent space to x, so that the determinant of the Jacobian is also efficiently computed. The determinant of the Jacobian is actually the volume, how much the volume is expanded when we go from one space to another space. And in the case of one-dimensional variables, it's just the derivative of this function. So here we have this latent space. The samples follow a simple probability distribution, which are independent of each other, and they are drawn, for example, from a logistic or Gaussian or uniform distribution. And through this function f, we map all this, or the sequence of random noise, to a sequence which sounds like speech. It's still a random sequence, because we transform a random sequence to another random sequence, but this has the characteristic of speech. For example, you can find the F0, the formants, and so on, which are characterized by the human voice. And also with the inverse transform, we can transform from speech to random noise, decorrelate this. I will describe a technique which is used in all that, in how to define the mapping F. This is called normalizing flows. The restriction on the mapping from latent space to observation space, the restrictions are so strong that it is questionable whether we can construct such a mapping. The mapping F should be continuous, invertible, efficiently computed, and for the determinant of the Jacobian should also be efficiently computed. Because this is important, because the dimension of x is the length of speech in samples, which is, for example, 100,000 or even more. And the same is this. So this is a matrix which has dimension something like 10 to the 6th or 10 to the 5, something like that. If you have a matrix with these rows and these columns, and in order to calculate the derivative, you need this kind of computation, this is prohibited. you cannot have an efficient algorithm. So you must find a function where the determinant should be diagonal so that to be computed very quickly. The normalizing flows is a powerful framework for building flexible posterior distribution through an iterative procedure. The idea is the following. Start from an initial random variable with a relatively simple distribution with known and computational cheap probability function, and then apply a chain of invertible parameterized transformation such that the iterate has a more flexible distribution which is more close to the distribution that we want to model. For example, we draw a sample x0, x0 from a known distribution, for example, a logistic distribution. We iterate sometimes. We put this as an input and we get zi, and we iterate this procedure. And finally, after some iterations, the zi belongs to another distribution which is very close to the distribution that we want to model. The conditions 3 and 4 to be efficiently calculated are satisfied if we choose as function, as a mapping, this affine, this transformation here, which is very simple transformation. It consists of the previous value times a multiplication with a non-linearity, and this is an affine transformation. So this can be easily computed with one layer neural network. Now we will see the inverse autoregressive flows. Inverse autoregressive flows are a special type of normalizing flows which are suited for high dimensional data. Inverse autoregressive flows can model a distribution as a transformation f of logistic. I use here logistic as follows. Initially a random sample is drawn from the logistic. All of them are independent of each other, and the following transformation is applied to z. xt equals f. This transformation is applied. The parameters here in this transformation are the following. The scale parameter and the mean parameter. This is a simplified transformation. But how we calculate these parameters? In order to transform this sample, we use all the previous noise values to calculate a parameter for scale and mean, and then we use this random value plus these two numbers, these two parameters that were calculated by this previous one in order to predict xt. And this prediction can be done in parallel. So it is very fast. For example, since we have all that from the beginning, when we calculate this at the same time, we can compute this one in parallel. If we have a GPU, we can compute all of them in parallel. That's why it is very fast. Let's see the Jacobian of inverse autoregressive flows. We need a Jacobian which is efficiently computed. The Jacobian is defined with this matrix here. If we take the derivatives and we use this transformation, we will see that the Jacobian is actually diagonal. It is all these upper are zeros and this lower triangular. And this kind of matrices, in order to calculate the derivative, is just the multiplication of the values of the diagonal. So it is very efficiently computed. You just calculate S1, the variance which was predicted, as I showed you before. What happens? We use these values which are calculated here, and this is nothing else than the sum of the log in the taking the logarithm is the sum of the logarithm. Without the logarithm is just the product of these values here. So it is very efficiently computed. So now I will explain how this is used, the whole algorithm. These are computed using the same convolutional autoregressive network structure as the original network. Another convolutional autoregressive network can also be used. In the paper of parallel wavenet, they say that we compute that without skip connections. However, in theory, even if we add the skip connections, the Jacobian remains lower triangular. So you may even use the skip connections. It's nothing wrong with that. The normalizing flows actually is this. We start from a sequence of samples taken from the logistic distribution, independent of each other. Then we apply 4 iterations. Doing that, all that can be done in parallel. The final distribution is logistic because one can show that if we apply this transformation, a logistic distribution remains logistic. However, all the initial logistic has 0 mean and unit scale, while the final distribution has a mean and a scale which is not always 0 and always 1, but it's time varying. And the mean actually has the form of the speech. If you take the trajectory of the mean, you will see that it has the form of the speech. And the scale is how far away this trajectory is from the original speech. How far away the prediction is from the original speech. In order to sample from this distribution, we do the following. We input the logistic, we input some sequence of noise, and then we apply this algorithm that I described you before and I describe you here again. In the paper of parallel wavenet, they use dilations and where the receptive field is this one, because the filter width is 3. So they use 4 layers of wavenet to construct the function f that maps from the samples of noise to the random samples that are very close to speech. Each one of these wavenet has the form of the wavenet together with the conditioning network, as I showed you before. In the paper of parallel wavenet, they say we don't have skip connections, so we have only one connection from here to the post-processing block. However, you can still add skip connections and you will still have similar results. So, we will see the training and generation of parallel wavenet. As I told you, the generation is very fast because it can be done in parallel. However, here we have the following problem. The training is sequential. It's sequential, it's very slow. It is sequential because of this. In order to evaluate the log likelihood from here, we have to convert xt to zt. In order to convert zt, we have to invert this function here to solve for zt, and this is the solution. The problem is, in order to calculate mt, we need all the previous random samples. The same for the parameter st. In order to do the inference, we are given this as an input during training. We don't have that. In order to generate that, we have to generate that sequentially. First we have to generate then this and then the next sample and then the next sample. So the training unfortunately is sequential and it is very slow. As a result, learning this inverse autoregressive flow directly through maximum likelihood is impractical. How the parallel wavenet is trained? In order to make the parallel wavenet training, they have proposed, not in the original paper, a lot of ideas. One is to use a loss function directly through the output of the network, which is that, and the target speech. However, comparing samples, the output of the network directly with the output speech is very poor measure and produces, if you train a network with that, it produces muffled speech. So this is, okay, this is a very, very simple loss function, and you can, for example, test your network if it works using this loss function, but the quality is not good. So if you want to synthesize excellent quality of speech, certainly this loss function is not the best idea. An idea that is used in the paper of parallel wavenet is to have two networks. An already trained network which is used as a teacher, and the parallel wavenet which is used as a student, and distill the knowledge of the already trained network, wavenet, to the parallel wavenet. This is an idea that is very common in machine learning. Usually in machine learning we have a huge model which learns a lot of things from huge amount of data, but this model is very slow in production. So we have also a very small model, and we distill the knowledge from the huge model to the small model, and the small model is very fast in production and loses only very small amount of information from the large model. So this is the distillation. In our case here, we do something different. We have a small model, which is the wavenet, and we want to distill the knowledge to a much larger model, which is the parallel wavenet. From the small model, we distill the knowledge to the larger model. However, the difference between this is the following. This one has sequential generation, and this one has parallel generation of samples, which means it is faster. And we measure how we do this distillation. Given a parallel wavenet student and a wavenet teacher trained on a data set of audio, the probability distillation loss, we have to find the output of this network and the output of this network and compare the two outputs, how far is the one from the other. This is the loss function. So we have to make the output of the student close to the output of the teacher. And the measure is this one, which is the Kullbach-Leibler divergence between the two distributions. This can be decomposed into two terms. The first term is this term here is the entropy term, which in the case of the logistic distribution has a closed form. And the other term is this term here, which is the cross entropy term, which in the case of the logistic loss probability distribution does not have a closed form solution. And we will calculate that through sampling.
Sorry, Vassilis.
Yes.
Can I ask, why do we order the terms in this way in the KL divergence? as opposed to switch them?
These two terms?
Yeah. No, sorry. Why do we calculate the KL divergence between the student and the teacher rather than from the teacher and the student?
How we calculate this? Divergence?
No, because it's not a metric, so it would make a difference whether we calculate DKL of between the student and the teacher, between the teacher and the student. Why do we choose this? As opposed to the other?
We have first the student and then the teacher.
Yeah.
The Kullbach-Leibler divergence, first of all, is not a symmetric measure.
If you
the teacher is already trained, does not change during the training of parallel wavenet. So if we put the other way around, this term will not make any effect at all. It will be a constant.
I think
yes?
it's that if you put it the other way around, then effectively you're just doing maximum likelihood again.
Yeah, never mind.
And so it's slow, because if it's PT to PS, then you're training PS using maximum likelihood, just maximum likelihood where the data is drawn from the teacher instead of from the data distribution, and so it's still slow.
Yeah, I see. This way we reward good entropy inside of student. Okay, thank you.
Okay. As I told you, there is no closed form solution for that, but we can sample using this sampling during training. However, if we use as an output instead of logistic the Gaussian, then this also has a closed form solution, an algebraic closed form solution. So the probability distillation works as follows. We have some random noise. We pass it through the student. The student predicts a probability for that. We use as an input this probability to the teacher. The teacher gives also a prediction of the next sample using that as an input, and then we compare this prediction with this prediction, and if they are far away, we penalize and we try to match these two predictions. Usually the probability distribution of the teacher is a mixture, at least in the original paper of parallel wavenet, is a mixture of discretized logistic, and the probability distribution of the student is just a logistic function. We have also some additional terms in the loss function. If you train only with the Kullbach-Leibler divergence, I will play you some samples later on, the quality is far away from a good one. So you need some additional loss function. At least you need the power loss, which makes the spectral information of the output of the teacher to be close to the spectral information of the target speech. We have also the contrastive loss, and there is also the contrastive loss and the perceptual loss. However, these two additional loss terms are quite complicated to compute, and they are not so important as it is this power loss, which is very simple to compute. Yeah. Is okay. No, it's okay. I will play you a sample. Here I trained a parallel wavenet using this loss. This is a very, very simple technique. You don't have a teacher and a student. You just have parallel wavenet. It gives an output, and you compare using this L1 loss with the target output. So it's extremely simple to, but you will see that the quality is far away from good.
How can you manage all alone, Mr.
It's muffled. However, this loss helped me to debug the network. Because imagine that you have to debug such a difficult program and at the same time to do training with a teacher and a student. It is impossible to find where is the problem. Here I debug the network. I was sure that the parallel wavenet worked okay. And then I try to do the training, student-teacher training, which is far away from easy. It's very difficult to stabilize this kind of training. I will describe this one. Here I will play you some samples from parallel wavenet. The first one is I use the Kullback-Leibler. I use only two loss terms. The Kullback-Leibler and the power loss. I didn't use the contrastive loss and the perceptual loss. Here the power loss is a very small value of the power loss, so the dominating term is the Kullback-Leibler. And you will see that without strong power loss, what is the effect?
Author of the Danger Trail, Philip Steels, etc.
You understand, but it's not very good quality. The same in everything.
Author of the Danger Trail, Philip Steels, etc.
Let's increase a little bit the power loss.
Author of the Danger Trail, Philip Steels, etc.
Author of the Danger Trail, Philip Steels, etc.
So if we compare these two terms, the Kullback-Leibler is very important to give you something that you understand, and the power loss is very important to give you something that is very close to human, because otherwise you hear this noisy background.
Vassilis, I've always been curious why that power loss term is necessary. Like, do you have any intuition as to why just the reverse scale training on its own doesn't...
What? The power loss?
Yeah, I've always found it interesting that the power loss is necessary to get good speech. Do you have any intuition why the reverse scale isn't enough on its own?
The Kullback-Leibler, possibly because speech with some noise, it seems that it has a very good score. For example, I don't know why, but even noisy speech, as you hear here, as you sound, they have even better score than the human speech. I don't know why. This is something peculiar. For example, possibly because of the entropy term that is also, the entropy term of the student that is also optimized. And if you have this optimization, sometimes when the speech is collapsed to noise, this term is improved instead of reducing. I really don't know the exact reason, but for sure, from this measure here, from this loss function, they pass all that things. And also, this and this have more or less similar value. For example, this loss function cannot distinguish between these samples and these samples. They more or less give the same value to both of them. But because the noisy are in a huge space of samples, because the noisy ones are much more prevalent and the good ones are fewer, it is more likely that you will converge to something like that than instead of something like that. So we use this additional loss function in order to help a little bit the model, because all of them more or less have the same value of Kullback-Leibler, to help a little bit the model to converge here. The problem here is the following. If you from the beginning uses a big power loss, then the loss function landscape is very complicated and you may get stuck in very poor local minima. So the training was really tricky in parallel wavenet. In that case, I managed to do the training. First, I trained with this model, and then I used that as an initialization, and increase a little bit the power noise to train the other one. I had convergence problems if I was trying to train that from the beginning. Possibly because of bad implementation, I don't know. I cannot explain. I'm not an expert in that field. I just implemented this algorithm and that's all. Are there any questions on that? Okay. If there are not questions, I will go to the final presentation of today. Which is Tacotron 2, and if there is time, I will also explain you the transformer, which is based on attention. The classical text-to-speech synthesis systems are complex. They have front systems. We have to do quite a lot of hand pre-processing, and all this system does not, how to say, cooperate very well one with the other. Recently, end-to-end neural networks, which are the state-of-the-art for speech recognition tasks, have become highly competitive also with conventional TTS systems. An end-to-end system can be trained on text-audio pairs with minimal human annotation and effort. It allows rich conditioning of various attributes such as speaker, language, sentiment, etc. It is more robust than a multi-component system. It has the potential of transfer learning and it can be adapted to new data. It may be trained on huge amount of often noisy data found in the real world. So, our problem is the following. We have some text and we may consider a regression function where the text is transformed into speech waveform. The classical pipeline of statistical parametric speech synthesis is that we have the front end, we have the statistical model in a statistical parametric speech synthesis, and we have the vocoder. The end-to-end problem is that to create a system that combines all that into one module so that the input has to be text and the output waveform. There have been many attempts to create end-to-end systems. Here are some of the attempts. I will say the Deep Voice 1, Deep Voice 2, Deep Voice 3, Tacotron, Tacotron 2, Carto 1, Voice Loop, Clarinet, and so on, many more. Deep Voice 1 and 2 retain the traditional TTS pipeline, which has separate graphem to phoneme, phoneme duration, frequency, and waveform synthesis models. In contrast, Tacotron, Deep Voice 3, Carto Wave employ the attention-based sequence-to-sequence models. In the literature, these models are usually referred to as end-to-end speech synthesis. However, they depend on traditional vocoder or a separately trained neural vocoder to convert the predicted spectrogram to raw audio. Clarinet, which is based on Deep Voice 3, seems to be the first text-to-speech, text-to-wave neural architecture for TTS. Here is the high level of Deep Voice 1 and Deep Voice 2. Here is the high level view of Tacotron 1, Tacotron 2, Deep Voice 3, and Carto WAV. You see that the Tacotron actually contains the front end, the statistical model, and some part of the vocoder, while the rest of the vocoder can be Wavenet, or the Griffin-Lim algorithm, or some RNN, or any other neural vocoder, or any other vocoder that converts from the internal, this speech representation that is produced by the Tacotron to waveform. And clarinet has this pipeline. From text, it gives directly audio. Let's see the Tacotron, which was one of the first very big successes in that area. The Tacotron, as I say, is not an end-to-end system, it's an almost end-to-end system. It maps from text to spectrogram or to Bell frequency bands. The vocoder can be the wavenet, or it can be the very simple Griffin-Limb algorithm, which is considered as a spectrogram inverter, which gives from spectrogram back to the speech. The algorithm is very simple. It's an iterative algorithm. It is described here. It converges after 30 to 50 iterations. It is very important algorithm because when we develop Tacotron, it allows us to debug the system without having to pass the data through a very complex vocoder such as Wavenet. So we can hear the results to see if our Tacotron implementation works. So for debugging the system is the best choice initially. However, for production, the quality of this spectrogram inverter is not the same as the quality of Wavenet. The high-level view of Tacotron is this one. This is the encoder, this is the decoder, and here is a post-net which improves a little bit the prediction of the decoder to produce the Bell spectrogram. The encoder is a bidirectional RNN, which takes an input sequence and produces a sequence of hidden states, which are better representation for the problem that we want to model, better than the input. The decoder is unidirectional. The encoder is bidirectional, while the decoder is unidirectional. The reason for that is the following. The encoder is a function which maps the whole input sequence to the whole hidden states in one time step. That is internally, works with recurrent neural networks is something that is only internal. It is not something that it is required by the model. So the encoder takes X and maps to Y the whole sequence X to whole sequence Y, while the decoder is autoregressive. In order to produce the next sample, we need first to generate that to use it as an input to this one. The decoder takes as an input some conditioning information which comes from the encoder and the attention model, which I will explain to you later on. So the decoder, the state of the previous time step, and possibly the output of the previous time step. So the decoder is autoregressive. So we cannot implement it with bidirectional, only with unidirectional neural networks. This is important since it is autoregressive. Let's explain a little bit what this context information is and how can we calculate that. In the literature, one of the first attempts to pass information from the encoder to the decoder was this. We have a recurrent neural network, and the last hidden state of the recurrent neural network, it is used as a context to condition the generation of the decoder. With three states in the encoder and a sequence of 3 time steps in the decoder, this works perfect. However, with longer sequences, such as the sequences that we have in speech, this construct is very poor for longer sequences. For this reason, the context vectors can be, they should take into account the whole sequence of the hidden states of the encoder. An attention mechanism assigns a probability to each vector in memory. Memory here is the hidden state of the encoder, and context vector is a vector that has the maximum probability assigned to it. It can be, for example, we calculate the similarity between the hidden state of the decoder and each one of the hidden states of the encoder, and we calculate these values here. The J runs from I to the number of input size of the encoder. And then we pass these similarity values through the softmax and calculate probabilities. We may take as a context vector the hidden state of the encoder, which gives the higher of these probabilities. The problem with this construct is the following. The probability distribution assigned to vectors in memory is not favoring a particular vector, is flat, especially at the beginning of the training. For this reason, a better choice, instead of using the argmax, is to take the mean. For example, to take the expected value through the hidden states of the encoder. And this mean is used as a context information to drive the generation of the decoder for the next time step. Here I will explain a little bit how we calculate the similarity between a state, the previous hidden state of the decoder, and each one of the hidden states of the encoder. We have this attention mechanism. The simplest one is just a dot product. A similarity is just a dot product. This was proposed by Luong. Then we have a slight generalization of this idea, and we have the multiplicated attention. The only difference here is that we have matrix V here, which are learnable weights here, and this allows us to have different dimension between the decoder and the encoder. And this matrix V changes from one dimension to the other. Another attention mechanism which works slightly better in practice than the dot product is the additive attention, which is this one. I will explain to you what this means. This is a learnable weight. These also are learnable weights. So we multiply the previous step of the decoder with a matrix. We have a value. We multiply each one of the states of the encoder with a matrix. We sum them together. We also add a bias. We pass through a nonlinearity. The value is multiplied with a constant V, and we produce this score. The location-sensitive attention term extends this attention mechanism to take into account the location. For example, this attention mechanism does not take into account where this IR, I mean, the same matrix applies to I and to I plus 1, so does not take into account in which position of time we are. So the location-sensitive attention, in that one, it adds this term here, which this term does a convolution, and the convolution is across time, where this matrix, where this vector AI are all the attention of the previous time step, how the previous time step calculated this attention. If you see the previous slide, it is these values here of the previous time step I minus 1. And finally, as you will see in many public implementations of Tacotron 2, people usually use cumulative attention. For example, instead of using AI alone, they accumulate the attention because they found that this is more stable and recovers more easily from errors. Also, there is a monotonic attention, but because we are not going to use that, and because of the time, I'm not going to describe it right now. Let's see the high level of Tacotron again. We have here the encoder, the attention mechanism, the decoder, which is quite complicated because it interacts with the location at the same time and has this feedback connection, and the output passes through a post-net, which improves the prediction of the decoder, and the output is the Mel spectrogram. The encoder, the first step is the input to the encoder are characters. Characters are represented by numbers from 0 to the number of characters minus 1 that we have. However, this is not a good input for a network. So we convert these numbers to a representation which is more suitable for neural networks, and we use embeddings. So, for example, let's suppose that we have character A, which in our system corresponds to number 0. So instead of putting as an input to the network the number 0, we choose the first row of this embedding matrix, and this is the input to our system. The weights of this embedding matrix are randomly initialized and are learned during training. Or you may use a pre-trained embedding table, pre-trained by another application. The encoder has some convolutional layers followed by a bidirectional recurrent neural network. The convolutional layers are very simple. They take the embedding, they pass through a convolution layer, then optionally there is a batch normalization. Optionally there is, this is important, we pass through a ReLU nonlinearity. After the ReLU nonlinearity there is a dropout which is also optional, and this is repeated I think 3 times. The function of this is that instead of representing one character, we represent a character with a context, because it takes into account the context through the convolution across the sequence, across time. The bidirectional LSTM is a very common LSTM. This is the LSTM unit, and we have a forward and a backward direction, and the output state of the encoder is the concatenation of the hidden state of the forward layer and the hidden state of the backward layer. It is important to have both directions, because if we calculate only, for example, let's suppose that we have only this state contains information from the beginning up to here. It does not have information for the rest of the time sequence. So this one has not information, if it is used only this, does not have information from the rest of the sequence. That's why we use bidirectional, because this one has information from the beginning up to here, and this one has information from the end back to here. So HT does not have information only from each time point, but also contains information, global information. That's why we use the encoder to transform from this sample here that only has information about its own to something that has information for XT also, and has additional information, it has also global information about the whole sequence inside it, which is much more suitable for the decoding task. And this is the high-level view of the encoder. This is the convolutional layers and the bidirectional LSTM. I think one good programmer, it can very easily implement the encoder of the Tacotron. It's not that difficult to implement the encoder. The attention and the decoder is slightly more difficult to implement and understand. It is quite complicated because inside the decoder we build the attention mechanism so that in each time step the attention mechanism gets input from the decoder RNN and gives input to the calculation of the next step of the RNN, and also inside the decoder we have this prenet, which in the paper it is described as an information bottleneck which helps to reduce the noise, and we have also this projection layer which projects from the hidden state to the output representation, for example 80 filter banks. And this is a more, we added also the post-processing net, which is outside the decoder. So it takes the whole output sequence of the decoder, and the function of the post-net is that to improve a little bit the prediction of the decoder. And this is Tacotron 2. Another network which has been proposed recently, which performs more or less the same in terms of quality as the Tacotron 2, is the transformer network. The transformer network has some advantages. First of all, it is much easier to implement than the Tacotron 2. The second advantage, the code for the transformer network already exists in the internet. Not the code, but the building blocks already exist in the internet. And I think they are common blocks in TensorFlow 2. They are included in TensorFlow 2 as a common blocks. This is a network which was first used in machine translation. Alexandros yesterday described you also the transformer network. In that way, the text-to-speech synthesis can be put in the same framework as the machine, as the translation from one language to another, from one sequence to another sequence. It can be put into the same framework. The encoder consists of a stack of self-attention and feed-forward layers, while the decoder consists of these two layers again, plus one more layer which is responsible to attend to the state of the encoder. For example, this is used to connect the encoder with the decoder. How the self-attention works. Let's suppose that the input is this, thinking machines. And after embedding, we choose these embedding vectors for thinking and this embedding vector for machines. From these vectors, we will produce some other vectors which we will call queries. How? We multiply this with a matrix V0 and produce this one. We multiply this with a matrix V0 and produce this one. We also produce some other matrices, some other vectors which we call keys. How? We multiply this with a matrix, this, and we produce this one. We multiply x2 with this and produce key 2. And we produce also values. How? We multiply this with this matrix and produce this one, and we multiply this with this matrix and produce this one. If we have this not as a separate vector but as a matrix, we can do the calculation of these two and these two in parallel, just matrix multiplication. So we may produce that in parallel using matrix multiplication. As I do here, I show you here that you can produce all that in matrix multiplication. And what is self-attention? Self-attention actually is described by this very simple mathematical formula. What we do? We take the input, we calculate with a matrix and produce this query matrix. We take the input, we multiply with WK and produce this key matrix. Then we compute key and query. So it's a similarity between these two. Actually, these two is the dot product attention that I showed you before. So this calculates the dot product attention, but with the additional, this scaling term, d kappa is the dimension of this matrix here. So we scale with the dimension just to improve the convergence. And we calculate this, we multiply this similarity measure here, which is a probability, if it passes through a softmax, is a probability distribution, with the values. So actually we give and calculate this z, which gives some, how to say, from these values we take the ones that are more relevant to our translation task. In self-attention also there is another notion which is called many heads. Instead of having only one such a self-attention, we may have several such self-attentions, 8 self-attentions, and do all of them in parallel. What is the benefit? If one computes something that is not very relevant, the probability that all the other of the 8 heads compute something that is irrelevant is very small. So some of them, it is expected, because we have random initialization, some of them we expect to find something good in the space that we are looking for. So this is how the self-attention with many heads is working. Each one computes something different, and then we concatenate all these values and we multiply with a matrix to find the final result Z, which is our self-attention output. And this is the whole process, how it works. One problem is the following. In languages and in speech, the position of one word in the sequence, it is important. For example, the position of this article here or somewhere else, it makes a difference because the context is important in languages. However, in self-attention, self-attention only takes account the word itself and does not take into account the position of the word in the sequence. And this is a serious drawback in the model. In order to alleviate this problem, it has been proposed to add to the embedding some other information, or concatenate or add to the embedding some other information which gives some information about the position of the word in the sequence. They have been proposed quite a lot of mechanisms. One mechanism that is used without trainable weights is this one, and this one uses sine and cosine to describe an embedding which has the meaning of time, and this encoding has the benefit that the position at time position plus k depends on the current position, multiply it by a matrix k, and this is independent of position. For example, if you are here and you go here and you go exactly the same interval, k time steps, the same matrix will be used to go from one position to something that is k steps in the future. It has this benefit. And the whole architecture of the encoder is this one. We have self-attention, we have layer normalization, we have skip connection here, and this is the feed-forward layer, and again we have normalization here and the skip connection. And the whole encoder and decoder mechanism is this one. If you compare that with Tacotron, this one is much simpler to implement. Here is an example of machine, how it works, of machine translation. It's again, the decoder is autoregressive. It produces one word, in our case in speech, one frame at a time, so it needs this one as an input to produce the next one, and so on. And now this is the whole transformer network, which is used in language translation from one language to another. We have the input embedding, we have here the encoder gives conditions the decoder, both of them are autoregressive with self-attention. We have here the output embedding, and we have the output probability. And if we compare side by side the Tacotron 2 and the transformer, we have these two constructs, more or less are the same. Here we have some encoder prenet and decoder prenet. We have this stop token, which takes a value below a threshold. When it takes a value during generation below a threshold, it means keep on producing output, and if it's above a threshold, we are already at the end of the utterance and it should stop. Both of them have this stop token. Here you can see this is a different picture from the one that I showed you before, because here we put as an input to the decoder of the Tacotron also the previous, we put these filter banks. This is a technique that is used to improve the convergence of Tacotron, and it is called teacher forcing. I will explain you what is teacher forcing. If we have a log sequence and from x1 we predict x2, and then from x2 we predict x3. If the prediction x2 is very wrong, then the prediction of x3, it might be even wronger. And it's very difficult to optimize this model. One idea is the following. Predict x2 from x1, let's say these are predicted, but instead of using x2 to predict x3, substitute x2 from the original value of the database while you are training to predict x3. And then, instead of using that to predict x4, use x3, the original one, to predict x4. This is called teacher forcing, and this helps a lot in the optimization. And actually, you may do mixed training. For example, throw a dice, and if the probability is above one threshold, do not use teacher forcing so that to leave the network to learn by its own, so that to predict the next one by the previous. And if it's below, use teacher forcing. For example, at the beginning of the training, use only teacher forcing. And as the training goes on and the network improves the prediction, then let the network use its own prediction to predict the next one. So you may use mixed teacher forcing. In the transformer, so here we have teacher forcing, so both more or less have very similar architectures. I will say very few things about other alternative architectures that are used for text-to-speech synthesis. One of these is Deep Voice 3. Deep Voice 3 is a fully convolutional attention-based neural TTS system. Deep Voice 3 matches state-of-the-art neural speech synthesis systems in naturalness while training 10 times faster. Deep Voice 3 uses residual convolutional layers to encode textual features into per time step key and value vectors for an attention-based decoder. The decoder uses this to predict the male band log magnitude spectrogram that correspond to the output audio, and so on. Hidden states of the decoder are then fed to the converter network to predict the acoustic features for waveform synthesis. And the clarinet, which is assumed to be the first true end-to-end system, and the high level of architecture of clarinet is shown here. Text-to-wave models convert textual features into waveform. All components feed their hidden representation to other directly, and so on. I only show you the high level without spending time on the details of this architecture. And this is the end of my talk. And if there are some questions, I will be happy to try to answer them.
Questions? You are going to do hands-on on this thing, so better to ask now the questions than during the hands-on.
Can I ask one question? In the self-attention mechanism, is d kappa much smaller than the input size usually? In the query and key matrices?
If they are much smaller than the input?
Yeah.
Not usually.
Because otherwise, wouldn't it be possible just to, why would we need to have a Q and a K matrix instead, if we are only using Q, instead of defining Q, K transpose?
Combining both of them together, you mean here? I understand your questions. For example, here you say that X VQ times X V kappa transpose means X is there? Yes, I will do it.
You can, that one, you can, yes.
Times, this is the Q, times it transpose and you say we can combine that to something like that.
Yeah, unless the...
You can do that, you can do that.
Okay. Thank you.
This is an optimization that you may do that.
A question on the transformer. Wouldn't be for the decoder really slow for speech creation, because you have to do like the attention over the whole thing with masks, right? I think it's gonna be like L squared on the complexity, where L is the length of your decoding. So for text should be fine, it is fine, but for like a spectrogram shouldn't be really slow, or?
This is a actually it is 4 to 5 times faster than Tacotron too. So for the length of the usual uteruses that we have, how many? Let's say 700 frames. It works 4 to 5 times faster than Tacotron too.
But it's correct that it's order t squared to generate, whereas Tacotron's order t.
You mean the complexity?
Yeah, but as you were saying, you have to do something at the sequence level for every frame that you generate.
Yes, you have to do all that. I have not implemented that algorithm. I only rely on the paper that describes. Actually, I am very close to implement that algorithm, but I have not yet finished. I rely on the paper that describes that, and these people say, it's from Microsoft Research, that it is actually in 4 to 5 times faster than Tacotron 2 when it's used in production, in synthesis, not in training. So I believe that. I don't know why it is faster. Cannot explain that.
Okay, probably there are no more questions, so thank you again.